This evening we're into our second ham radio lesson here, and I just wanted to go through a couple of components and a little bit on AC and DC voltage as a demonstration of the class. Just at the end of the course for tonight, one of the components we took are capacitors. So in capacitors there are several basic constructions of capacitor. Most of them are round because they're created using two pieces of tin foil with a layer of wax paper in between as the electrolyte, the dielectric rather. The capacitors that are rolled up like this usually have a band indicating the outside foil, and usually this lead with the band goes to ground or to negative. That's very important when you get into electrolytic capacitors. The band is negative ground because they're marked with a positive as well. These come in very high values, like what do we got here? 100 microfarads, whereas these are only a quarter of 1 microfarad. When you change that electrolyte inside the dielectric and make them into electrolytic capacitors, they can come in very high values. At the other end of the scale, for very small values, I don't know if this shows up or not on camera, here's one that's only 2 picofarads, very, very small. We used to call this 2 microfarads, 12 decimal places. Some are made of ceramic, one example, and others are extremely old. Here's one from the mid part of the 20th century that even has a color coding on the capacitor, like the resistors that we all know. But these can be no longer found. They don't use color coding on capacitors anymore. Just an example of how things work. Certain capacitors have air as a dielectric, and they are more commonly used as tuning capacitors. For instance, here's an LC tuning circuit. This particular one is used for an antenna tuner. And the coil, for instance, has taps on the coil that are selected by a switch on the front, and that gives you a variable inductor. So you got variable XL. For variable XC, capacitor reactance, you can change the mesh of the plates on the capacitor. So you can change the inductive reactance, you can change the capacitive reactance, and where they meet, that's resonance, and that's how you tune things, right? Easy stuff. The other thing I wanted to go through tonight was a small bit on AC voltage. DC voltage is easy, but AC voltage, it's explained a little bit better if you can put it on an oscilloscope. Here's a very old scope, transistorized, but quite old. And what we've done here is just put ordinary household current, 60 hertz, about 110 or a little bit more here in Canada. And what you're looking at, it doesn't come out to 110 volts. If you'll notice, when it's set up here at 50 volts per centimeter, and each one of these lines vertically is a centimeter, you've got 50, 100, 150 volts up from the 0 line in the center, and 50, 100, 150 volts down. So the peak to peak voltage on this thing is 300, a little more than 300 volts. And how do we get that from 110 volts? What's actually happening is that 110 volts that you took up in your books is the root mean square, RMS. And that's 1.414 times, sorry, the peak value is 1.414 times the root mean square, whereas the RMS is 0.707 times the peak value. So you can get a pretty good belt off 110 volts. There's over 300 volts there. Just wanted to show you that part. If you wanted to stop the camera for a second,